Okay, so let's make a start. So where are we in the lecture notes? So we're still on chapter 1, part 1, and we were talking about combinations. So let's just remind ourselves, what is a combination? So the idea is you have n distinct objects and you choose r of them, and you're interested on how many possible combinations there are, and a combination doesn't really take into account the ordering. So we had an example somewhere here. So in this example, we have 4 letters A, B, C, and D, and we take 3 of them, okay, without replacement, right? So when we choose 3 of these 4, right, if you look at this first column, first row, excuse me, they all contain A, B, C, but each of the orderings do not count as distinct combinations. So there's just 4 combinations here, not 4 times 3, 24 permutations. So permutations, we count the ordering. In combinations, we don't care. And so what we had done in the previous lectures, we derived this formula for the number of combinations when you're taking R objects from N. And that was this formula, n choose R. So I call this thing on the left-hand side n choose R, and it's called the binomial coefficient. It's defined as you see in front of you, n factorial over n minus r factorial, where 0 factorial is equal to 1, and we're going to define them only for integers, non-negative integers. Okay, and so where we got to, so we got to page 113. So we had done this bad apples example. So we're moving on, and we're just going to basically apply the formula for combinations. So we have several examples more to understand this formula a little better. Okay, so example 2. So what does it say? It says you have 4 women, from 4 women and 3 men. You want to find the number of committees of size 3 which can be formed that have precisely 2 women and 1 man. Okay? And so this is unsurprisingly going to be a combination of 2 things that we've learned. So the combination of combinations and the multiplication rule. Okay, so the first part of the solution, which is this thing at the top of page 115. Okay, so the number of ways of selecting 2 women from 4 is 4 choose 2. That's exactly what we've just been talking about. It's 4 choose 2. So that's 4 factorial over 4 minus 2 factorial and multiplied by 1 over 2 factorial. So that's 6. Okay. And then you want to select 1 man from 3. So that's 3 choose 1. That's what that formula is. And that's 3 factorial over basically 1. So that's equal to 3. 3 factorial over 2 factorial, excuse me. So then basically the total number of ways in which this committee can be formed is the multiplication of these 2 terms, right? You've got this number way of selecting 2 females from 4 females and 1 male from 3 males, and I multiply the 2, and that's the total number of committees that can be formed. Okay, that's what it's asking. Okay, example 3. So example 3 is a kind of variation on exactly the same question, except there are some restrictions or non-restrictions in this case. So you have 4 men and 5 women. You want to get a committee again of size 3, but now what you have is you have no restriction. Okay, that's part A. And part B says, well, let's look at part B and see when we get to them. So part A. So the number of committees that could be formed, well, this is simple. You have 9 individuals, 5 males, 4 females, I believe. And the other way around, yes. And you're just going to choose 3 individuals from those 9. So that's 9 choose 3. I don't care who I get, I'm just going to get them, and that's the total number of committees that I can get. Okay. Now part B asks the question, with 2 men and 1 woman, if a certain man must be on the committee, right? So you have to have a particular man has to be on the committee, and then how many committees can I form in this case? Excuse me. This one is relatively straightforward, okay? So since a particular man must be on the committee, we can only choose 1 man from the remaining 3 men to the committee. Okay, so the number of ways to choose 2 men to sit on the committee with a certain man in the committee, was it 2 men, is that right? 2 men, yes, okay. So the number of ways of choosing 2 men to sit on the committee with a certain man in the committee already is going to be 1 choose 1, well, that's no, because that's only one way to choose that individual. Now what happens here is you have 3 men left over, and I can choose any of them. So there are three possible additional men that could be chosen. So there are for the men that are in the committee, there are 3 possible combinations. Now for the females, it's a little bit easier because there's no constraint, because now I only have 1 female in the committee, and I've got 5 females. If I've got 5 choose 1 possible women I could select. Okay, so that's going to be 3 times 5 choose 1, which would be 5. So 3 times 5 is 15. Okay. Now part C is a bit more complicated because it asks us the following. So now the committee again must be 2 men and 1 woman, but the two of the 4 men are feuding, so we can't have them on the same committee. Okay, so they cannot be on that same committee. Okay, so how do we do this one? Okay. So, there are 2 choose 2 times 5 choose 1 ways to form a committee in which 2 particular men serve together. So the idea is we're going to take the difference, right? So we know the total number of committees that we could have. And so we don't want that so we know already, right? So if we wanted to produce part 2, so if you want to now form a committee, the total number of committees you can choose overall would be of 2 men and 1 woman would be 4 choose 2 times 5 choose 1, right? That's the total number of committees with 2 men and 1 woman, right? But this scenario which I've just described to you is not the thing that we want. We want actually the case where that doesn't happen. So we just take the total number of committees, we subtract it by what we don't want to happen, and that gives us what we do want to happen. So that gives us 25. Okay, so one more time, just in case you're unclear, this is the total number of committees that can be formed with no constraints, where you have 2 men and 1 woman. This is the case we don't want to happen, so the difference gives us what we do want to happen. So there are 25 such committees where this could occur. Very good. Okay, so example 4. So this one, actually the wording is a little bit confusing, so I'll try to explain it as well as I can, but basically the idea is that you have a bus company, and they have developed cracks under the bus. Okay, that's this part here. And now, a particular company has 20 of these such buses, and there are cracks in 8 of them. Okay, so now part A asks us the question, how can you select a sample of 5 of the 20? Okay, and this wording is rather confusing, so you could just think of it as being this stuff in blue. I don't really think that this thing helps us understand what it is that's being asked. So that's quite straightforward. So part A is 5 choose 20. There's nothing more than that, right? I want to choose 5 out of 20. Part B is more interesting. So in how many ways can I take a sample of 5 buses and contain exactly 4 with visible cracks, or the cracks under the bus, right? So the number of ways of selecting 4 buses from the 8 with visible cracks is, of course, 8 choose 4. Okay, this is the formula for 8 choose 4 on the right hand side. And the number of ways of selecting 1 bus from the remaining 12 with no cracks, is 12 choose 1. Okay, so that's 12 choose 1 because I'm choosing 1. 12 buses are fine. Okay, so then the resulting answer is going to be 70 times 12. So that's 840, apparently. Okay, example 5. Example 5 is to do with bridge, and actually it's a little bit confusing if you don't know how to play bridge. I don't know how to play bridge myself, but apparently it's a hand of 13. You take 13 cards. And the question asks, how many bridge hands are possible which contain 4 spades, 6 diamonds, 1 club, and 2 hearts? And these things could all happen simultaneously, by the way, because these things, they could all happen simultaneously, right? Because there's 13 cards. Okay, so the number of possible hands that you could get. Okay, so of course with 4 spades, there are 13 spade cards, so 13 choose 4. There are 13 diamond cards, so that's 13 times 6. There's 13 clubs, so that's 13 choose 1. 13 hearts, that's 13 choose 2. And they can happen all at the same time. That's why we use the multiplication principle. So if you multiply all those things together, I mean, it's a bit of a tedious thing. I mean, to be honest, like I say, if I was going to give a solution, I would stop here. But if you want, you can put the numbers into the calculator and get the exact solution in terms of numbers. It's quite a lot. Okay. So that was combinations. Hopefully those, what was it, 5 examples, I think. 5 examples. Hopefully that made the formula clear. It's basically n choose r, and basically all the examples were just using a combination of the multiplication principle and precisely that combination formula. Now what are we going to do? So now we have understood some basic things about counting up things, right? Counting up how many things can happen. Now why is that important? Because now what we're going to try and do is to construct sample spaces and the notion of probability so we can start to try to model events, right, or a random phenomena, or constructing sample spaces over possible things that can happen, right? That's basically what we want to do. So that counting stuff, so it doesn't make, if you're trying to understand what's the connection of that to probability, well, it's going to help us enumerate sample spaces in events in order for us to formulate the notion of probability. Okay, so there is an interpretation of probability. Actually, I don't subscribe to this, but that doesn't matter what my personal feelings are about probability. It doesn't matter. We'll think about it that way. And the idea is essentially the following. So we have this notion of a random experiment, an experiment where we don't know what's going to happen, right? Obviously, if we know what's going to happen, there's no point of using probability theory. And so we don't know what's going to happen. And if we consider an event A associated with the experiment, then we basically, what that means is we cannot state with any certainty that A will occur, because if we can, again, there is no reason to use this kind of mechanism. So basically what we're going to try and do is to associate to every event of interest, or that we can evaluate, or lies in a particular class, in fact, how likely that is to occur. Right? And that's going to be essentially the notion of a probability. Now, what does this thing mean? Okay, this does not matter too much. So this is basically what is the theory of probability. It's essentially assigning the likelihood, how likely something is to occur, associated to an experiment where we don't know what will occur. Okay? So, for example, if I flip a fair coin in the air, well, if it's fair, what it means is it's equally likely to be heads or tails, so probably I will assign the probability a half to a head and a half to a tail. So this is the notion of a probability, and we're going to formalize this. This remark here we will probably see later today. So probability can be derived, being the operative word, based upon the notion of relative frequency. So the idea is this. Suppose I have an experiment and I repeat it a multiple number of times. Okay, let's say I do it n times. So here, flipping a coin. So let's say I flip a coin 10 million times. And then I count the number of times that a head lands. Okay, so in my example here, the experiment E is flipping a coin. N is 10 million, I think I said. And A is the event, which is I'm saying is that the coin lands as heads. Okay. Then if I count the number of times that heads lands, let's say that's 5,000,001, okay, then a definition, if you like, or an interpretation of probability is through the notion of a relative frequency, which is basically the number of times the event happened divided by the total number of events, the total number of experiments that I compiled. So in my example, I got 5,000,001 heads. I flipped the coin 10 million times, so that's roughly 0.5, and that's going to be my interpretation of a probability. So this is a relative frequency, and the relative frequency is one interpretation of probability. And like I said, it's not one I subscribe to, but anyway, that doesn't matter. So this relative frequency, which we called f subscript a, that's just the number of times the event occurs divided by the total number of experiments, is a number, and of course it's at most 1, because I could, the best scenario of my coin flipping experiment is I could have, or the best, once perhaps an unlikely scenario is I flipped the coin 10 million times, and 10 million times it was a head. So it's at most 1, and the other extreme would be that in my 10 million flips of the coin, I never saw one head. Okay, so a relative frequency by its very definition, right, it's NA over N, that can be at most 1, but it's at least 0. Okay, and as I've explained it ahead of time. FA equal 1 means that basically it's essentially called a sure event, because basically that always happens, or has always happened in our experiment, or repetition of the experiment, and FA equals 0, meaning it never occurred in our repetitions. Okay, so let's think a little bit more about this. So this is basically an interpretation which is going to cover over to probabilities, relative frequencies or probabilities for some people. So if A and B are two mutually exclusive events, what does mutually exclusive mean? Remember that if I take events A and B, sets A and B, and I take their intersection, and if their intersection is empty, we said they are mutually exclusive, okay? So then the relative frequency of two mutually exclusive events basically is equal. So if I think of the union of those things, that's equal to the sum of the relative frequencies. So in my example, it's a very strange example. If I take heads and A is heads and B is tails, and I'm interested in the relative frequency of the heads or tails occurs, well, of course, that's the ratio of the number of heads to the number of experiments plus the ratio of the number of heads, tails to the total number. And that's actually equal to 1 in my example. The notion is that if I did, n was large enough, huge, millions and billions and trillions, if we like to say that, then basically that frequency should stabilize, or one believes it should stabilize. In my example, it's reasonable to assume that if I flip my coin for 1 billion times, probably something close to 500 million times I'll get a head, because I have a fair coin. And that interpretation is essentially going to be what a probability means. It means how often, essentially, if I was to repeat the experiment many, many times, this is how likely I am to see a particular event or outcome. Okay, this is an interpretation of essentially what it is that this sentence says. Okay, so this limiting quantity is going to be called a probability. Okay, and a probability, if you like, is just a long-run relative frequency. Okay, if that makes any sense to you. If it doesn't, well, it doesn't matter. We'll just start from the beginning, right? Which is what I prefer, because I don't believe in that. So we consider an experiment, flipping a coin, which has a sample space S. Remember sample spaces? Back this time last week, we talked about the event, the collection of all possible outcomes of an experiment. That's called a sample space, S. And so the objective of probability is to assign, for each event A, a number PR of A. I prefer, this is the notation we're using in this course. So what this notation, so PR is probability in the brackets inside the element inside the brackets, the argument, A is the event. So this means the probability that the set A occurs, and it reflects the long-run relative frequency of that event, if you like. Okay? And if you like, it's how we, in probability theory, quantify uncertainty. Okay? So, for example, probability is an absolute thing. I can compare probabilities. So if I have two events with numbers 0.1 at 0.9, then of course the event with probability 0.9 is much more likely, 9 times more likely to occur. Okay, so it gives us a nice way to compare the likelihood of events. Okay, so the third bullet point, so P is just a notation. So P, what it means is the collection of events. That's all events, okay? So that has a technical name, actually. It's called a sigma algebra, but you don't have to know that. That's not important. If you like, so what is curly P? Okay, the thing that I have my marker on my hand on, if you like, that's the collection of all possible events which I'm interested to make probability statements on. Okay, and so for us, that's basically any event we can think of. Okay, in technical terms, it's not always true, but it doesn't matter. Okay, so this is literally a set of sets. Okay, just think about what that means. Okay, so probabilities there's a notion of a probability space. There are three things you have to have: the sample space S, the collection of events on S, and that's a set of sets, and PR of A, which is basically the probability distribution over those sets in curly P. Okay, so for every event A, there's a rule that if you give me an event A, I return you back a number between 0 and 1, which reflects precisely how likely that event is to occur. Okay, And this is just a base notion of probability, but there are some particular axioms meaning basically rules which we define from the beginning, for which this probability distribution PR of A must satisfy. And they are as follows. So axiom 1, these are rules, all right? There's no proof for this. We define this thing, and this gives us a calculus, or if you like, a set of rules for which us to perform probability theory. Okay, there are 3 axioms. It's very likely one day you will be asked what those are, more than likely in this course. The first axiom is, as I said, that the likelihood or the probability or the long-run frequency, relative frequency of an event A is a number which is at most 1 and at least 0. Okay, so this is very important. You can never get a negative probability. You can't get a probability bigger than 1 by definition. Please never write that down. If you do anything, if you don't understand a word of what I say, or you don't understand the notes, just for my sake, please don't write down a probability bigger than 1 or less than 0. You cannot get it by definition. Okay, it is an absolute number. It tells us, it gives us a way to compare how likely one event is relative to another, right? That this is something you can't always do, but in this scaling, it is basically available. Okay, axiom 2, rule 2, okay, is that the probability of the sample space is 1. Okay, so the sample space is the set of all possible outcomes in our experiment. Okay, so the chance that something happens is 1. That's the interpretation of what this axiom or rule means. Something must happen. Okay. Okay, axiom 3 says the following. It says, okay, so there's some technicalities here, but let me explain it to you. It shouldn't be too difficult to at least understand, even if you're not happy about it. It's a definition, right? We're defining this to be true. So the first line of this says, I take a sequence of sets. So A1, A2, they're sets, events. Okay, they belong to this set P. And they're mutually exclusive. What that means is if I take any pair I and J, okay, I and J are not equal, I take the intersection of those 2 sets, I get back the empty set for every pair I and J which are not equal. Okay, so these are all mutually exclusive events. The interpretation in words is these events cannot occur simultaneously. Okay, now there's countably infinite of them. What does countably infinite mean? That means that I have a sequence A1, A2, A3, A4, and if I was still here tomorrow, I'd be in A557. You see, this goes off to infinity. So there are many, many sets. This thing actually can occur. And what does that mean? Okay, well then, basically what this thing says, this is a rule, which is that I take the probability of the union of all those sets. So remember what this notation means, right? We covered that this time last week. This means just the union. So I take an element which belongs either to A1 or to A2 or to A3 or to A4. So I want the probability of this countably infinite union. Okay, this is the mathematical phrase. It basically means what's the probability of A1 or A2 or A3 or ... Okay, and so this axiom, what it means in words, is the probability of this countable union is just the sum of the probabilities. And it's a definition, okay, only for mutually exclusive events. Okay, so that says, for in particular, so if you're not clear understanding what it is, I'm talking a special case of this axiom is if I take A and B, 2 mutually exclusive events, what this means is the probability that A or B occurs, okay, I'm talking about this line here, is precisely equal to the sum of the probabilities. Okay. Now, given this collection of 3 axioms, it will be very surprising how far you can go from this. We can define probability rules, or we can work out probabilities for a wide class, in fact for everything. This is all we need this is essentially all we need, of course, without going into technicalities. Okay, so let's have a look at some examples. So let's have a look. So I've started with, I think it's the easiest thing to think about. You consider an experiment, you flip a coin and let H denote the event of having a head. Okay, it asks us the following: find the probability of H, PR of H, that's what this thing means here, if the coin is fair, if the coin is biased and a head is twice as likely to appear as a tail. Okay, this one, okay, so again, we will cover this in more formality later on, but this one is relatively intuitive. So, from our axiom of probabilities, we take the set S, which is the set HT. Okay, sample space is S. Okay, this is our collection of all possible outcomes, head or tail, right? We know that the probability of the sample space is equal to 1. That's our axiom number 2. We know that H and T are mutually exclusive events. So we know that the probability of H plus the probability of T is equal to the probability of H union T is equal to the probability of S. So the probability of H plus the probability of T is equal to 1. Okay, that's where that equation comes from. Here I've done nothing more than use the fact that of axiom 2 essentially and axiom 3. Oops, excuse me. Okay, now the coin is fair. What that means is that it's equally likely that I get a head or I get a tail. So those probabilities, P of H plus PR of H plus PR of T, must be equal. Okay, so now if I solve this equation, so this is simple simultaneous equations, you probably did it in school very many years ago when you were 10 or 11 or something like that, or even earlier. So I substitute this thing into this equation, and if I rearrange, of course, then I will get the solution that the probability of the head is equal to the probability of a tail is equal to 1 over 2 if I have a fair coin. Okay, now we're asked the question is to work out the probability that a head occurs if it's twice as likely to appear as a tail. Okay, so this is 2/3. Why is it 2/3? Okay, so we are told that the probability of a head is twice as likely to appear as a tail. So basically now what we have, this equation here, it still holds, right? That they haven't done anything to this scenario other than this. But we now have the fact that the probability of a head must be equal to 2 times the probability of a tail. Okay, so now if I substitute into this equation here, which I still have, and rearrange for PR of T and then substitute in to get the probability of a head, it's very straightforward, then I get that the probability of a head is 2/3. Okay, simultaneous equations, nothing more than that. Okay, so that's example 1. Example 2. A fair die is thrown. What it means is basically each side is equally likely to fall on. Each side is equally likely to fall down, right? A is the event that an even number turns up, and let B be the event that either 1 or a 3 occurs. We are asked to find the probability of A, the probability of B, the probability of A union B. So note that straight away A and B are mutually exclusive, right? Because A is the set 2, 4, 6, B is the set 1, 3. Okay. So the sample space is 1, 2, 3, 4, 5, 6. I can roll a 1, 2, 3, 4, 5, 6 on my 6-sided die. A is the set 2, 4, 6. Those are the even numbers. The probability that A occurs, well, probability of A occurs is 1 over 2. Because basically, with a fair-sided die, a fair 6-sided die, the probability I get 2 is a sixth. The probability I get a 4 is a sixth. The probability I get a 6 is a sixth. They're all mutually exclusive, so the sum of those is equal to, the probability of this event is equal to the sum of the probabilities. So I get a 6 plus a 6 plus a sixth. That's equal to 3 over 6 is 1 over 2. Okay, and similarly for B, B is the set 1 and 3. The set 1 and the set 3 are mutually exclusive, so the probability of the set 1 and 3 occurring is the probability of the set 1 plus the probability of the set 2 is a sixth plus a sixth, so that's equal to 2/6, which is a third. Okay, so then finally A and B are mutually exclusive because there is no element of A which belongs to B, so the probability of A union B is equal to the sum of the two probabilities. Okay, that's that's basically axiom 3. It is axiom 3. So now I add a half and a third together and I get 5/6. Okay, very good. Okay, now we're still in example 2. Example 3 is example 2, except we have one additional event. And C is the event that you get a number divisible by 3. So I basically roll a 3 or a 6. Okay, I'm asked to find the probability of C occurring, and I'm asked to find the probability of A or C occurring. Okay, so now remember that the sample space is the set 1, 2, 3, 4, 5, 6. C is the set 3 and 6, with 3 and 6 are divisible by 3. The probability that C occurs, of course, is then just the sum of this probability plus this probability. So that's a sixth plus a sixth. So that's equal to 1/3. Now, A union C is what? Well, I have this, A was what? Well, let's remind ourselves, it's 2, 4, 6. C is the set 3 and 6, so if I add them together without repeating, the union of those two sets is 2, 3, 4, 5, 6. So I have my 3, I have my 6, and A presumably has 2 and 4 in it. So union. So now I have 4 elements of A union C is 2, 3, 4, 6. The probability of this is then just 4 over 6, because that's the probability of this one plus this one plus this one plus this one. So it's 2 over 3. Okay, very good. Now, just an important point to make. The probability of A plus the probability of C, I can compute that. That's a half plus a third is 5 over 6. Right? Because the probability of C is 2, 6, and the probability of A was 1 over 2. Okay? But that's not equal to the probability of A or C. And that's important. Why? Because we have said in this example, you can note that A and C are not mutually exclusive. Why not? Because there are elements in C which belong, I take 2, 4, 6. Okay, so I have the number 6. So C and A have an intersection. That means which is non-empty. So they are not mutually exclusive. So axiom 3, this rule which I've just introduced to you here, does not hold because you do not have mutually exclusive events. Okay. Oh, that's it. Okay, very good. Okay, so that's the set 1. Okay, so we now move on to the next part. Okay, so this is now pages 137. I'm still doing basic properties of probability. Okay, some basic properties of probability. So now we saw some 3 examples. I think they were relatively straightforward to understand. If they weren't, please let me know. And what's going to be very surprising here is the fact that we're going to be able to derive several probabilities of events only using axioms 1 to 3. Okay, it might be surprising. I don't know how surprising it is. Maybe you don't find it surprising, but it might be. So the first property, so we're going to derive something like 5 properties, I believe. The first one is that the probability of the empty set is equal to 0. This is what this red thing says. Okay, I'm telling you that that's true, but I can justify it. Okay, so again, phi is the empty set. It contains nothing. Okay. Okay. So what's the justification? Okay, so I take A1, A2, A3, my sequence of sets, which are basically empty. Okay, so then if I take the union of those sets, they are, of course, empty. Okay, so now, by axiom 3, the probability of the empty set is equal to the probability of this countable union, because it's countable union, and so this one here means that this set and this set are equal, so the probability of this set is equal to the probability of this set, because this set that I'm putting my hand on is exactly this one. Okay, now they're mutually exclusive, okay, because basically the intersection of phi with itself is phi. Okay, so of course they're mutually exclusive, so the probability of this countable union is the sum of the probabilities. Okay. Right, the probabilities of AI, what is it? Well, AI by definition is the empty set. So for every subscript I in the summation, I get the empty set. So for every element of the summation, I got the probability of phi. So what this thing says is the probability of phi, which is the left-hand side, is equal to this infinite sum of the probability of phi. So this thing on the right-hand side is actually infinity unless the probability of phi is equal to 0. Okay, so this thing can only hold, this can only be equal to this. In the only scenario it can hold is if the probability of phi is equal to 0. Otherwise, if this thing is non-zero, i is 0.1, this right-hand side is infinity, and that cannot happen. Why can't it happen? Probabilities are numbers which are less than or equal to 1 and greater than or equal to 0. Okay, so it cannot be that this number is anything different from 0. If it were, this equation cannot be holding, but it does hold by construction. Okay, each of this step is true because this set is equal to this set. This step is true because these sets are mutually exclusive. Okay, and that's axiom 3. It's our rule. Okay, this one is true because this one is equal to this one. So this construction is true and can only be true in the case where the probability of the empty set is 0. Okay, I said that twice just to make sure it was clear. Okay. Right. Okay. Property 2. Property 2 is fairly straightforward to understand. It's a special case of axiom 3. Okay. So this says the following. I take A1, A2 up to AN. Okay. N here is a fixed number. It could be 3, it could be 25,606. Okay. It's fixed. And they're all mutually exclusive. That means if I take the intersection of AI with AJ for any IJ in the set 1 to n where I is not equal to j, I get back the empty set. Okay. Then I claim that the probability of the union is equal to the sum of the probabilities. Okay, and you're going to say, so what? Well, the reason so what is why is it useful? Because basically this is just a special case of axiom 3. So it kind of seems like it should be true, and it shouldn't be too hard to establish on the basis of our axiom 3. Okay, so how do we prove this one? Straightforward. Suppose that AN plus 1 is defined to be the empty set. Suppose that AN plus 2 is defined to be the empty set. Suppose that AN plus 3 is defined to be the empty set, and I keep on doing that forever. Okay, so now what do I have? I have my original collection of n sets, A1, A2 up to AN, and I have this collection as this is essentially an infinite sequence of sets, except when I start the index from n plus 1, I'm always empty, and n plus 1, n plus 2, so on and so forth. Now, consider the probability, so consider the union of these sets, I is equal 1 to n. I'm interested in this event. Okay. By definition, or well, not by definition, by construction, this countable union of, it's countable and it's finite union of A1, A2 up to AN is precisely equal to this countably infinite union because the additional sets which I've introduced into the sequence are precisely empty and do not add anything, if you like, to the total mass of the overall set. So this is equal precisely because of this. Okay. Right, now I'm in business because now I don't have much to do left in order to establish this property 2. So the probability of the union from i's 1 to n of the AIs is precisely equal to the probability of this infinite union, precisely because these two sets are equivalent. Okay? Now what do I do? Now you can note that precisely all of these events AI are exactly mutually exclusive. Why? Well, if I take the intersection of any of these, they're empty. If I take the intersection of this one with any of these or this one with any of these, it's empty because this one is empty. This one is empty. They're all empty. So all of the events, A1, A2, up to AN, AN plus 1, AN plus 2, off to infinity, they're all mutually exclusive. What does that mean? Well, what it means is when I have this event here, right, all the events are mutually exclusive, so I can apply precisely axiom 3, which says that this probability of this countably infinite union is precisely equal to this countably infinite sum. Okay. Now, what do we know? We know the probability of the empty set is 0. That's property 1. So, basically all terms in this summation from n plus 1 off to infinity are 0. So basically this sum of probabilities is equal to the sum I is equal 1 to n of the probability of the AIs. Okay. So that's property 2. Okay, property 3 is intuitive. What does it say? It says the following. I take any event A which belongs to that set P. It's never mentioned again actually, but P. And I asked about the probability of the complement of A. This is, remember what the complement is. This is the prime notation for complement. A complement is I take the set A and then I take the sample space S and then I remove everything of the sample space which A has, and that gives me A complement. Or if you prefer, everything which is in A is taken out of the sample space. And this property 3 is the probability of A complement is equal to 1 minus the probability of A. Okay, and it makes sense, right? It should make sense because this is everything that's not in A. This is everything that's in A. Okay, how do we establish this one? Well, we know immediately that the sample space S is equal to A union A complement. Okay, I take A, I add on everything in the sample space which is not in A, and I get basically the sample space. Okay, if you've forgotten, we actually covered this in last week's lecture. Now, AA intersection, that's empty, right? Why is that empty? Because A complement doesn't contain any element of A. So the intersection A with itself is empty. So what does that mean? So the probability of the sample space S is the same as the probability of A union A complement, precisely from this identity that I've just explained to you. Okay, because A and A complement are precisely mutually exclusive, the probability of A and A complement is equal to the probability of A plus the probability of A complement. Okay, they're mutually exclusive. Okay, very good. So the probability of S is 1. That's by definition. Remember that that's axiom 2, apparently. Axiom 2 says the probability of S is 1. So the probability of A plus the probability of A complement is equal to the probability of S is equal to 1. So the probability of A complement is 1 minus the probability of A. I just rearrange the equation that we have there. Okay. So that's probability 3. So we've got a few more. If you just, okay, how many more? A lot. Okay. Probability 4. So let's look at probability 4. So the probability 4 says that the probability of A is equal to the probability of A and B plus the probability of A and B complement. Okay, this one should be pretty straightforward to understand. So why is this the case? Okay, so look at this identity here. So if you look at this identity here, the thing that's going to help you to understand everything that's going on here, if you really just don't have a clue what I'm talking about, well, you can go back and have a look at this. These are some basic properties of operation events, right? So you remember last week where I was saying complement, union, intersection about 10,000 times? Well, now it's going to come into handy, okay? So remember, so here what we are doing, okay, so here we have A is equal to A intersection B union A intersection B complement. Well, that's precisely this property 10, okay? So I've not just plucked that thing from the air. I explained it to you to an extent in last week's lecture. Okay, so now this is the case. We also know that if I take this event here and this event here, their intersection must be empty because this event includes B and this event includes everything in B or some element of B complement. Okay, so the intersection of this set and this set is precisely empty. Why is that important? Well, because the probability of A is equal to the probability of this set. The probability of this set, okay? And this set and this set are disjoint, i.e. they are mutually exclusive, so the probability of A is equal to the sum of this probability plus this probability. That's exactly the quantity, that's exactly the property that we wanted to establish. All right, very good. Okay, I'm just going to look at property 5, then we will have our break. I can understand that properties are now beginning to get a little bit dry, so we will have one more and then we will have our break. Okay, so now let's look at property 5. Property 5 is kind of interesting in some sense. Interesting. I mean, it is interesting because it says that I take the union of A and B. A and B are arbitrary events. They need not be mutually exclusive. Then the probability of A plus the probability of B minus the probability of A and B is equal to the union. Okay, so what we say is for any events, so note this formula holds true in the case that A and B are mutually exclusive, because if they're mutually exclusive, the intersection of A and B is empty. So the intersection of A and B is empty. That means that this thing is the empty set. So this means this thing is 0. So it holds in the case of the mutually exclusive events A and B. Does it hold in general? Well, let's establish that. Okay, so let's have a look at this. So here I claim A union B is equal to this. Okay, you're going to say, where did that come from? Well, let's have a look. So I think if you look at this equation 9 and you interchange the role of A and B, you will get precisely this thing here. Okay. If I can call this one B and this one A, and I'll get the same equality. So you just have a look at number 9 if you're wondering where it comes from. Okay, now the intersection of these two events is precisely empty. Why is that? Because B intersection A intersection B complement must be empty, right? Because you have to have everything in B and B complement at the same time. It can't happen because it's empty. So, what does that mean? So now I'm interested in the probability of A union B. I have this nice decomposition. This decomposition is nice because these two events, A and B complement, are precisely mutually exclusive. So I take the probability of the union, it's just equal to the sum of these two probabilities. Okay, very good. But property 4 tells us something. So this is the equation I have so far. Okay, but it's not giving me very much. If I look at this equation here, I haven't got very close, have I? But I know something about the probability of A. So let's have a look at what we just looked at. Property 4 tells us this. The probability of A is the probability of A and B plus the probability of A and B complement. That's what I just spent a few moments explaining to you. Okay, so this is the same thing. I've written it down there. So now, if you substitute for the probability of A and B complement, so the probability of A and B complement, that's equal to the probability of A minus the probability of A and B. Okay, so in this equation, that's what I've obtained so far. If I substitute for this with the probability of A minus the probability of A and B, I get that the probability of A union B is the probability of B plus the probability of A minus the probability of A and B. And that is exactly the property that I wanted to establish. Okay, so that's property 5. So we'll take a break now for 5 minutes and we'll resume at 51 minutes past 2 and we'll go back. We'll be on page 142. Thank you. Okay, so let's resume, please. So we've just got a couple of properties left over, 6 and 7. It looks, well, 6 and 7. It looks more horrible than it is. But basically what we're doing in the following is building an equation, a general equation for the probability of the union of an arbitrary number of countable sets, a finite number of sets. Okay, so in property 5, what did we do? We derived an equation for the probability of A or B occurring for any pair of events A or B. Okay, what we're going to do in property 6 is the same job, except we have 3 events A, B, and C, and there's going to be a property 6A, which is going to have an arbitrary number of finite unions. Okay, so this property it reads like this. I won't read it out, but it's basically the sum of the probabilities of A, B, and C. You subtract the pairwise, 2 of the pairwise intersections, all the pairwise intersections, and you add on the 3-way intersection. Okay. And in fact, for general n, it's called the inclusion-exclusion formula. It doesn't matter at this stage. Okay, so we're going to verify this equation, and unsurprisingly, we basically use the property 6. Okay, so property 5. So if you have the union for 2, the basic notion is going to be that we have A or B or C. Okay, and I want to find the probability of the union. Well, of course, the union of A, B, or C is the same as the union of A with B or C. Okay, this thing is an identity. You can check it. It's the kind of distributive law that we investigated last week. So now what we're going to do is we're going to apply property 5 when this is my set A, if you like, and this is my set B, even though this is B or C. So let's use property 5. So the probability of A or B or C, this one, is equal to the probability of this event. And now I apply property 5. So this probability, this is the one I have here, is the probability of A plus the probability of B or C minus the probability of A and B or C. Okay, very good. Okay, now what can I do? Well, I know something about this one, this blue, excuse me, I don't know if you can see this, this one here, the probability of B or C. Now I know the probability of B or C because that's the probability of B plus the probability of C minus the probability of B and C. Okay, so I apply property 5 again. Okay, so this one was already there, this one was already here, and I've just substituted for this one using property 5 again. Okay, very good. So now you look at it and you say, well, it looks a little bit like what I claimed at the beginning, right? I've got the probability of A, the probability of B, and the probability of C. I've got those, that's very nice. I've got the probability of B and C, that's very nice. But now I've got this term which looks horrible, and I've got these terms which are not the same. Okay, so I'm clearly not finished yet if this thing is to be true. Okay, now the probability of A and B or C, well, we can use the law of distributivity. This set here, it's exactly this set, right? So this is the same as A and B or A and C. Okay, this is one of our properties, I think. If we look at this back here, it's basically using this thing here. It's like this. You just mix these things up and look exactly the same, but that's the thing. Oh, it's exactly the same. It's just using this type of a thing here. Okay, so now what does that mean? Well, now I have this event A and B union A and C. So now what am I going to do? I'm going to use property 5 again. So that is that the probability of this union is the probability of this set plus the probability of this set minus the probability of the intersection of these sets. Okay, very good. So then the next line, well, I don't do anything to this one, I like the look of it. I don't do anything to this one, I like the look of it. And now I look at this one. Now I look at this event, A and B and A and C. Well, the intersection of that highlighted set is the same as A and B and C. Okay, so this thing here, okay, so again, just to justify this equation, all I have done is I've used one of these properties here. This one I've highlighted, I believe. Well, not this one, I think. Right, this one here. And then I've just applied property 5. And then I've just used the property of this set, that this intersection is the same as the intersection of all of these 3 sets. So what does that mean? Well, that means the following. Well, if I look at this is what I've done so far, okay? And basically what I'm doing is I'm playing around with this thing here. And we've derived that that thing here was equal to this. So now if I substitute for that formula, what do I get? Well, that means that the probability of A or B or C is the probability of A plus the probability of B plus the probability of C minus the probability of B and C. And then I subtract the thing that I just got, which is minus the probability of A and B minus the probability of A and C plus the probability of A and B and C. Okay. So it's just... basically, the trick here is to use this property 5 and then just some properties of sets. So that can be extended. So this formula is holding in the case where you have an arbitrary number of n events. It looks like a horrible formula. Okay. You don't need to be able to derive it. You can derive it if you want. I can derive it for you if you like, but it's not very... It's not very difficult, to be honest. The way in which you can establish this formula, it's just a formula. It's called the inclusion-exclusion formula. It's not very particularly pleasant to look at. But basically, the way in which this formula can be proved, well, what we have done is we have proved this formula. If you want to check it, you can take the case n is equal 3, right? That's what we've just done. We've proved this formula in the case n equals 3. This is what the formula looks like, right? So you can do what's called mathematical induction. You've also done the case n equal 2 as well. So then what you do, how do you prove this formula? You assume the formula to be true in the case k, all right? N is equal to k. And then you consider the case k plus 1. Okay, so then you basically have to prove k plus 1 given k and your properties 1 to 5 and your axioms. Okay, that's what's called mathematical induction. You don't need to have to do it here, at least. I don't think it's really, this is not that type of course. It's just formula is written down for you. Okay, it's you'll never use it. I mean, to be honest, it's so tedious to use that you will never use it beyond n is 3 anyway. So, but you have it if you need it. Okay, now, property 7, it's our last property before we do some examples. If A is contained in B, then the probability of A is less than or equal to the probability of B. Now that seems obvious because we know that everything lies, so this, remember what this thing means. This means that everything which is in A is also in B, but B might have something extra. Okay, so what that means is so it's intuitive that the probability that A occurs can be at most the probability that B occurs if A is contained in B. Okay, so it seems intuitive and it's true. Okay, let's have a look. So now, remember that we just used this one, so B, for any event A, is equal to the union of B with A and B with A complement. Okay, remember we said that just a moment ago. Now, so this, by the way, that's true. We used that a moment ago. That's true for any sets A and B. But we have something special because we know A is contained in B. So if I take the intersection B and A, I'm going to get back A, right? Because everything in A lies in B. But B might have something extra. Okay, so this red highlighted term, that's precisely true because A is a subset of B. So, what does that mean? Well, B intersection A, that's equal to A, so I substitute here. And then this thing is as it was before. Now, what do we know as well? We know those two events, A and B and A complement, are disjoint, or they are mutually exclusive. Okay. Very good. Okay, so now what do I want to do? Well, now I know I can express the probability of B. The probability of B is equal to the probability of this union. This union is disjoint, so it's equal to the sum of the probabilities. Okay, so now what I've shown is the probability of B is equal to the probability of A plus the probability of B and A complement. Very good, you say. So what does that mean? Well, you know that the probability of B and A complement is at most 0. Okay, so this expression on here on the left-hand side, I guess, is at most the probability of A. It's greater than or equal to the probability of A. But this number could be bigger than 0. Okay, so that's why this thing is bigger than this one. Why is that useful? Because that's shown exactly the thing we wanted to do. Because the probability of B is greater than or equal to the probability of A, which is exactly what we want to do. Okay, so this here, so again, this expression is always non-negative. It could be 0, but it's possibly bigger. And once it's possibly bigger or bigger than 0, then this expression must be bigger than this one. Okay, and that's equal to the probability of B. All right, very good. So we've seen these 7 properties. It looked like it would never end, but they did. So let's have a look at some examples and try and see and apply these formula, which we've maybe understood. At least we've seen them. Okay. So the first example is the following. So you have a retail establishment. They either take American Express, Amex, or they take Visa. Or either of them, actually. That's very exciting. So now we're given some information. I don't really... Yes, okay. So you say a total of 24% of individuals, they carry an American Express card, and about 61% of the individuals carry a Visa card. Okay, that's probably about right. And about 11% have both. Okay. Now, the question is, what percentage of the customers carry a credit card that the establishment will accept? Okay. It's a bit of a conundrum, really, isn't it? Let's have a think about that. Okay, so now we introduce ourselves to our 2 sets, A and V. So A represents the event that a customer carries an Amex card, American Express, and V is the event that the customer carries a Visa card. And what we are told, okay, if we were to interpret our percentages as probabilities, is the probability that an individual has an American Express card is 0.24. Okay, that's this thing here. The probability that an individual has a Visa card is 0.61. That's this information here. And 11% is that they carry both, so that's the probability that A and V is equal to 0.11. Okay, very good. Now what are we asked to do? We want to compute the probability that they have either an American Express or a Visa card. So that, well, we know what this thing is equal to. That's property 5. The probability of A union V is the probability of V plus the probability of A minus its intersection. Oh no, and we're in such a good situation that we know the probability of A, we know the probability of V, and we know the probability of A and V. Because the probability of A, that's 0.24. The probability of V is 0.61. The probability of A and V is 0.11. We substitute this into this equation, I get 0.74. Okay, and then the interpretation, the solution, if you like, he doesn't say it, is that there's roughly 74% of the customers carry a credit card the establishment will accept. Okay, it's kind of strange thing to think about, really, but there you go. Okay, example 2. You have a pool of statisticians. Okay, let's return this full screen. We have a poll of statisticians in the USA. They was conducted to work out what their professional responsibilities are or were. So an analysis of their responses gave the following distribution of professional responsibility. So 40% had the set, or they had to do some research. 64% had a professional consultation, and C, which was data analysis and connection, and that was 36% of people. Okay, very good. So now it says, suppose that 20% are involved in all 3, 15% are involved in A and C, and 17% are involved in A and B. Okay, that is basically giving us lots of excitement there. And using this information, find the percentage of all statisticians in the USA that are involved in both B and C, and we are told to assume that the probability of the union is equal to 1. Okay, so what do I want to compute? I want to compute the probability of B and C, and I multiply it by a factor of 100, and that gives me my percentage. Okay, so how do I do this? Okay, well, it's not unsurprising we're going to use this property 6, which is the probability. Well, let's work out what we know first. Okay, so we know the probability of A and B and C is 0.1. How do I know that? This is what this information tells us. Okay, so this first sentence here, 10% are involved in all 3 activities. The probability of A and C, well, A and C is even told us here, 15%, 0.15, and A and B is 0.17. Okay, so that's the information we've got. And now, what do we want to do? So now we know the probability of A or B or C. We apply our property 6, that's the probability of A, plus the probability of B, plus the probability of C, minus the 3 intersections, plus the three-way intersection. Okay, we are told precisely that this number on the left-hand side is equal to 1. Okay. Now, what do? Well, we want to know the probability of A, the probability of B, and the probability of C. Well, that's precisely here, right? This is supposed to be the probability of A is 0.4, the probability of B is 0.64, the probability of C is 0.36. Excuse me. So I substitute in here, this is the probability of A, this is the probability of B, the probability of C, the probability of A and B is 0.17. The probability of A and C is 0.15. Probability of B and C, I don't know that. I want to find that. And then the probability of all three is 0.1. Okay? So now if I rearrange this equation for the probability of B and C, you can see it right in front of you. Apparently it's equal to 0.18. Okay? So that's the solution to example 2. Example 3. Okay, let's have a look. Example 3. So they're all kind of the same kind of question, really. But anyway, so the probabilities that a gas station pumps gas into 0, 1, 2, 3, 4, or 5 or more cars during a certain 30-minute period is 0.03, 0.18, 0.24, 0.28, 0.10, and 0.17. You sum those numbers together, they should give you 1, otherwise you'll get some very funny answers. And now the question asks us the following. Find the probability in this 30-minute period that more than 2 cars receive gas, that at most 4 cars receive gas. Okay, so let's start with A. So this is a kind of simple type of idea. So here you introduce this notation A subscript I. That's the event of pumping I cars for I equal to 0, 1, 2, 3, and 4. A5 has a special meaning because that's the event of pumping 5 or more cars. It's kind of a funny type of terminology. So know that all the AIs are exclusive, mutually exclusive, right? I can't pump 0 cars and 1 cars at the same time. I can't pump 2 cars and 4 cars at the same time. These are all in the intersection of each of these AI is precisely phi, the empty set. Okay, so now this asks us what's the probability that more than 2 cars receive gas? So the probability that more than 2 cars receive gas is the probability that 3 cars receive gas, or 4 cars receive gas, or 5 or more receive gas. That's what these 3 events mean. They're all mutually exclusive, so the probability of their union is the sum of their probabilities. Okay, and then these probabilities, they're given to us on the previous slide. Okay, so we just add these numbers together, and the answer to B is 0.55. Part B says at most 4 cars receive gas. So there are a couple of ways you can do this. We're going to do it the tedious way. So the tedious way says the probability of at most 4 cars receiving gas is the probability that none of them do, 1 of them do, 2 of them do, 3 of them do, or 4 of them do. Okay, and then they're all mutually exclusive. So the probability of the sum of the probability of the union of these events is the sum of their probabilities. Okay, we know that already. We've derived that. I think that was probability 2 or something like that. And then I just add these numbers together. Okay, that is a kind of the most tedious way to do it. If you want to do it a slightly more clever way, the probability of at most 4 cars receiving gas is 1 minus the probability of 5 or more cars receiving gas. Okay, I know this number, that's 0.17, so this thing is 1 minus 0.17 is 0.83. Either solution is correct. The second one is far less tedious. Okay, very good. Okay, example 4. So I apologize for the phrasing of this example. It's a little bit, I think, sexist in this day and age, but just think of these as being numbers. I'm sorry about this. Is a beauty pageant, which I don't think really is a kind of very politically correct thing to have anymore. But anyway, apparently Audrey is taking part in a Halls pageant. I don't know what that is for, but anyway. The probability that she's supposed to win is 0.14, and the probability that she's going to win Miss Photogenic is 0.3. Okay. The probability that she's going to win both is 0.11. Okay, so now we're asked 2 questions. What's the probability she wins at least one of the 2, and what's the probability that she wins only one of the 2? Okay, so this is just basically playing around with English words. So part A. So A is supposed to be the event that she wins the crown. B is the event that she wins Miss Photogenic. So the first one is she wants to win at least one of those 2. So the probability of A or B occurring, of course, is the probability of A plus the probability of B minus their intersection. So now we know the probability of A, that's 0.14, the probability of B is 0.13, and the probability of their intersection is 0.11. Okay, so I substitute those numbers in, I get 0.33. Part B. So part B wants the probability that she wins only one of the two titles. Okay, so that's A or B minus, set minus. Okay, what that means, what does this mean? Okay, if you don't know what this thing means, it's a little bit, well, it might be confusing, but basically I take A or B and I remove the probability of A and B. Okay, and I claim that's equal to the difference of these two probabilities. Okay, why is this one true? Well, I don't know that we ever justified it. I'm not going to justify it to you right now, but I can give you an intuition as to why that's true. Let's see if today my telestrator works. Sorry, it worked earlier, so give me a minute, please. Okay, so basically the idea is that you can take. Okay, there we go. So it's not going to be very exciting. I'm just going to draw a plot. Okay, so I'm taking. So this square is the sample space. Okay, I'll use blue to help. Okay, that's the sample space. That's supposed to say S. Okay, this is the set A, and this smaller set is the set B. So this is B here, and the whole. So it's not supposed to be anything too deep. Basically, the square is everything that can happen. The big circle is the set A, which includes the set B. So B is a subset of A, and B is the small thing. Now, if I'm asked about what's the chance, the probability that B A set minus B occurs, okay, then intuitively the probability of A set minus B, so what is A set minus B? Well, it's actually this donut-shaped ring, okay, so that intuitively, I'm not giving you a proof of it, that's equal to the probability of A minus the probability of B, okay. Sorry about that, it's there. Okay, so what do I mean to say by that? Well, what I mean is in this scenario where B is a subset of A, okay, so this is just the difference between these two probabilities. A is bigger than B in my example, right? I take this set, this is this big circle A, I take the smaller set, which is this small circle B. I'm interested in the set, the probability of this set. So intuitively, the set that's left over when I take this one from this one is just this donut ring. And so intuitively, the probability that A occurs is the probability of A minus, the probability of A minus the set of B. The probability of this donut ring occurs is the probability of A minus the probability of B. There is a way to prove it, but I don't want to do that because I think that's just intuition is enough. In our example, okay, so we go back to the notes. In our example, A union B is set here. It's bigger than A and B, right? This is everything in A and everything in B. This is just the combination of the two. Okay, so that's one way of thinking about it. Okay. Again, I haven't proved that formula. So, I know the probability of A or B, that's 0.33. The probability of A and B, well, that's 0.11. So the difference is the solution is 0.22. So again, that's the answer to part B. Okay, very good. So example 5, actually example 5 is interesting. So the very first class that I've had in probability, okay, I'm a mathematician or at least a statistician, the first class we were taught the birthday problem. I always thought it was a load of nonsense, but it's kind of interesting. I think some people think it's interesting. It's kind of nice in some sense, but it's actually an example. It's called a hypergeometric distribution. We haven't learned that yet, so don't worry about that. So this is the question. So it's a party trick. I don't think it's a party trick, but anyway, I mean, you know, sort of maybe a dull party. So basically you've got a room, and they've got at least 50 people there. And what you claim is that you think two people share the same birthday, How often are you right? Okay, I don't really like this phrasing. I don't know, acting awesome is something you should do after this. So you can cast that as a probability question. Okay, so this is the question. So there are n people in the room. What is the probability that at least 2 share the same birthday? Okay, it turns out that if n is moderately high, it's actually quite likely. Okay. So let's first of all make a model. So our model is that there is only 365 days a year, and we don't take into account leap years. That's just basically to simplify a model. This is the first example, one of the first examples you're thinking about, where actually we're making an approximation of real life. So we're saying a year is only 365 days. Excuse me. A person can have their birthday on any one of those days, right? So basically, the total number of different outcomes is 365 to the power n. That's a multiplication principle. Person 1, 365 possible days. Person 2, 365 possible days. Person 3, 365. I do that at n times, and I get 365 to the power n. Okay, that sounds like it's massive, so you would think as the larger n grows, well, this can't possibly happen, that 2 individuals have the same birthday, but of course there's only 365 days, so that's the key. So that's the size of the sample space, if you like. Now we introduce a set A. It's the event that there are at least 2 people among the n sharing the same birthday. Okay, so that's what we're really interested in. But what we're going to do is we're going to work out the probability of the complement, which is the probability that no 2 people share the same birthday. And once we work out that, we then know the probability that 2 people share their birthday, because that's 1 minus the probability. Okay, so this is what we want. This is what we're going to calculate. And once we've calculated this probability, we're going to get this one. Okay, how do we do this? Now what we're going to do is we're going to do, so all this counting stuff that we spent last week talking about counting this and that is going to come in handy. So now this cardinality, so what this means is, by the way, I didn't really say what this thing, so this hashtag means basically the cardinality, the size, okay, the number of elements which lie in the state space. So this is what this thing means. Sorry, I didn't say that. So the cardinality of A complement, that's the number of elements which lie in this set A, which is the event that no 2 people share the same birthday. How do we work out that? Well, we take person 1 and we let them have any day of the year, 365 choices. We take person 2. Now that person can't have the same birthday as person 1, but they still have 364 choices. We take person 3, then that person can't have the same birthday as person 1 or 2, so now they have 363 choices, and we keep on doing that until we get to the nth person. Okay, so that's how we get the cardinality of the size of the set A complement. Okay, so again, it's a multiplication problem. It's exactly what we covered in last week's lecture, I believe, or one of last week's lecture. So now what we're going to do, we're going to interpret the probability that A complement is going to be the cardinality of the size of the state space of A complement divided by the total cardinality. This is our relative frequency type interpretation. Of course, there are many models you can build for this problem, and this is the one we're doing, or we're going to do. So the probability of this event, that's the cardinality of the size of the state space of A complement divided by the size of the state space. Okay, if you like, it's just this expression here divided by the expression that we wrote here. Okay, so the probability of A occurring, the probability of A occurring is 1 minus the probability of A complement. So I do 1 minus this expression, and I do some simple algebra. This expression is not important how you get it. It is an expression, but you can see that it's a product, and it's an n product almost, n minus 1 terms. And of course, calculating this for anything more than 3 or 4 is tedious, but you can do that very fast on a computer. Okay, so this is what we did. Okay, so remarks. So you cannot compute this for a given n. I mean, you can compute it, but it's very easy. But you wouldn't do it on a piece of paper, and you wouldn't even do it in a calculator. But you do it in a very simple computer program. So n, that's the number of people in the room. Okay, so the probability of A is, this is P of n. This is what I care about. That's the probability that 2 people have the same birthday. So obviously, in the case n is 1, well, there's no chance there's only one person. Obviously, that makes sense. Now, you can see that as n grows, once you get to about 50 people, the chance that basically 2 people have a birthday under this probability model, and it is a model, is 0.9, it's basically 0.98. Okay, so that's what it's saying. So 98% of the time you'd be right in this party, if you could call it that. Note that the probability of having 2 people sharing the same birthday exceeds a half, once you have 23 people. So I guess we're supposed to have 100 people here, so that would have been an interesting thing to do, but now I guess we've only got 20 people, everyone watching it on video, if they're watching it at all. So we were probably in this case rather than the first case. Okay, very exciting. The inverse birthday problem. Inverse birthday problem is not something I'd ever heard of until today, but this is what it is. How large a group of randomly selected people have to be such that the probability of someone is sharing his or her birthday with you is larger than 0.5. Okay, so I'm now saying, okay, how big do I have to make this group so that I have a good chance of sharing the birthday with me? So the probability that n people all have different birthday from you is 364 over 365 to the power n. Why is that? Well, basically my birthday is on, let's say, 26th of October 1979. Now, basically, or 26th of October, which is basically what it wants. And then basically, if I take another person, the chance that their birthday is on 26th of October is 364 over 365 under my model of 365 days. Then basically, we're assuming that essentially, then the probability of the next event is the same 364 over 365, and I multiply them through together. In fact, we haven't studied how to obtain this probability, but we're assuming something here, that the probability that any individual has a birthday which is different from mine is independent of anyone else's, but otherwise you can just believe that that's this kind of cardinality result. Okay. Now what do I need? I need this number to be at least 0. I need the 1 minus this number, right? Because I'm asked the probability that someone is sharing their birthday. So 1 minus this probability to at least be 0.5. Okay, so I can rearrange this equality. I take 1, I take the 0.5, I take the other side. This is for me it's a natural logarithm, so I take a natural logarithm, and eventually you get an inequality for n. Okay, I'm sure you can rearrange this. If you can't rearrange this, please let me know. I will do it on the board for you. It seems like you can. Okay, so if I just rearrange this equation, I will get that I should have at least around 253 people, excluding yourself. Very good. So why is there such a big difference in the answer to those 2 birthday problems? Well, this inverse birthday problem requires the sharing of a particular day. The birthday problem is allowing that any day is shared. Okay, so remember that we were having here 253 people, not 253 days, and before in this one you have 50 people, right? And that's because there's basically any day that you can share. All right, very good. So we've got about 10 minutes left, so let's just finish up. I would like to think a little bit more about sample spaces having finite outcomes. Okay, so we consider the sample space S. Okay, so this is basically a generalization of the things we talked about when rolling die or flipping coins. Okay, this is a generalization. So this construction contains those 2 scenarios. So we consider the case we have a sample space and it has a finite number of k outcomes. Okay, and you might say, well, that sounds particularly boring, but it's actually, there's surprisingly very many probability models where you can explain phenomena which are non-trivial, which still have this setup. Okay, so you can go, so you're computer scientists / engineers, but if you're a physicist, there's something called the Ising model. Ising model is used to model spins of atoms. Okay, the outcomes in this model is actually finite. It's big, but it's finite. Anyway, so that is to say, our sample space S constitutes k possible items, A1 up to AK. Okay, and the probability that AI occurs, AI is a point in the sample space, is defined to be p subscript I. Okay, so what do we know about this construction? Well, the construction, we know two things at least. One, which is that the pi, p subscript I, is again at most 1 and at least 0 for I in the set 1 to k, for every I. Okay, that's because it's probabilities. This thing is the probability of this thing. This is an event. It's a point, it's an element of the sample space, so it's an event. And so the probability that it occurs is at most 1 and at least 0. And we know that the sum of all these probabilities, they have to be equal to 1, because this is the probability of the union of the AIs, and the union of the AIs is equal to S, and the probability of S is equal to 1. Very good. Okay, so now let's think about the following. We take an event A, and it consists of a collection of outcomes A J1 up to AJ subscript R. Okay, R is in the set 1 to K. What does this mean? Well, this is maybe A1, this might be A5, this might be A9, and that's it. Okay, these are just this notation. If you don't like it, this subscript is just any collection of indices which are different from each other. Okay. So A1, A2, A3, A5, A7, A9 are examples of such a set. Here I'm taking R equals 3. Okay, now what do I want to do? Now I'm interested in computing the probability that this set A occurs. Okay, so A subscript J1, A subscript J2, and so on and so forth. These are mutually exclusive events. So if I'm interested in the probability of A occurring, that's just equal to the probability of this one occurs plus the probability of this one occurs plus ... plus the probability of this one occurs. So that's P subscript J1 plus P subscript J2 plus ... plus P subscript JR. Okay. Now, what am I talking about? Well, if you recall, if you look back, this is the construction we've been using when you think about flipping coins, for example, or rolling die. So remember that we were saying, okay, this could be that I want to roll a 2 and a 3, right? So this is my set A. So the probability of the set 2 and 3 is the probability of rolling a 2 plus the probability of rolling a 3. So that's why that's a third. That's another way of thinking about it. That's just what I just explained is an example of this construction. Okay, and that's basically what he's saying there. That's what I've just said. Okay, let's have a look at an example. So this is more complicated, but basically just keep in your mind that basically that's the same as the case where we rolled a die or flipped a coin or whatever. So here I take a sample space S, which is the sum of the numbers when a pair of fair die or dice are thrown. Okay, so you can see all the possible outcomes. I can roll these are the possible outcomes of rolling the 2 die. The sample space is not just, this is not the sample space, this is just all the possible outcomes of rolling 2 die. Okay, it's a wonderful size of 36 elements. But the sums can be, well, of course I can get 2 here, I can get 3, I get 4, and so on and so forth. The sample space, it turns out to be 2, 3, 4, all the way up to 12. The maximum number I can get is 6 plus 6. Okay, so if you're wondering what does this thing mean, well, this thing, what it means is a 5, 5, I rolled a 5 and I rolled another 5. Okay. All right, now if I'm interested in the probability that 2 occurs, that's the probability that I roll 1 and a 1. Okay, that's the only scenario here that I can do that. Now if I'm interested in the probability, so the probability that, what's the probability I rolled a 1 and 1? Well, there's 1 over 36 elements. All elements are equally likely, so it's 1 over 36 if you prefer. Well, let's not prefer, let's just do that. What's the probability that I roll, the sum is a 3? Well, the sum is a 3, I get this situation, 1, 2, but I have another case where I get 2, 1. So there's 2 cases out of my 36. The die is fair. It doesn't say that, but it should be. So there's the probability of P of 3 occurring is 2 over 36. Okay, I'm not going to do all of these. I can see you're already sleeping, but let's have a look at one more of these. Let's look at the probability of the set 9. So what does the set 9 mean? That means the sum of my 2 die is 9. Okay, so when does that happen? Well, that happens when I get a 3 and a 6. 6 and a 3 is here somewhere, I swear it. Here it is, 6 and a 3. I get a 4 and a 5 and a 5 and a 4. So I get 4 over 36. Okay, and so on and so forth. Okay, if there's an element of here you don't understand, you can ask me. Okay, now let's suppose the event is A, which is 5, 7, and 8, and 11. So that means that the sum is a 5, or a 7, or an 8, or an 11. So the probability that A occurs, well, we'll just apply this principle. The probability that the 5, the 7, the whatever it was, you just sum those numbers together, 5, 7, 8, and 11. Okay, those numbers are calculated in this table here of 12 items. So apparently P5 was 4 over 36, P7 was 6 over 36. Okay, P8 was 5 over 36, and P11 is 2 over 36. You add those numbers together, and that gives you the probability of the set A. Okay. Let's try and finish this example. If we don't, we'll finish on time. Anyway, so we have now a dice. It's loaded. That means, what it means is that an even number is twice as likely to occur as an odd number. If E is the event that a number is less than 4 on a single flip, find the probability E. And I don't think we'll have a time to do B, so let's just think about A. Okay, so A is asking us to find the probability that the number is less than 4 on a single roll of the die. So the probability of S is 1. Okay, the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5 plus the probability of 6 is equal to 1. Okay, because the probability of S is just the union of those elements. Now we're also told that the probability of an even number is equal to 2 times the probability of an odd number. So if we say that the probability of rolling an odd number is P, then this term here is going to be P. This one is 2P. This one is P. This is equal to 2P, this is P, and this is 2P. Now you add them all together, you're going to get 9 times P. You rearrange, so P is equal to 1/9. Great. What's the answer to the question I'm asking? The question I'm asking is, what's the probability that you get a number less than 4 on your single die? So E is a set 1, 2, 3. So the probability of E is the probability of 1 plus the probability of 2 plus the probability of 3. That's equal to 1/9 plus 2/9 plus 1/9 is 4 over 9, 0.44 reoccurring. Okay. I think with 2 minutes and the look of everyone's faces, I will spare you any more. So I'll see you tomorrow at 2 o'clock in LT28. Thank you very much for your attention. We're on page 170.